For decades, physicists viewed light as a continuous, flowing wave, but experimental evidence eventually exposed a different reality. Light also behaves like a particle, delivering energy in discrete, quantifiable hits. This behavior is central to the photoelectric effect. Light doesn't arrive in an unbroken stream. It strikes surfaces in distinct packets of energy, ejecting electrons one by one. In 1905, Albert Einstein named these packets photons. He proved that these particles of light carry both energy and physical momentum. This created a glaring contradiction. Light has no mass, yet it collides and moves like a tangible object. In the quantum world, pure radiation acts like matter. If a massless wave can act like a physical particle, it raises a symmetrical question. Can solid matter act like pure energy? That was the inquiry posed in 1924 by the French physicist Louis-Victor de Broglie. De Broglie reasoned that nature is built on symmetry. If the universe allows radiation to behave like matter, those same rules should apply to physical mass and motion. He proposed the concept of a matter wave, asserting that all moving particles display wave-like properties under the right conditions. This hypothesis bridges the gap between mass and electromagnetic radiation, suggesting they are two sides of the same coin. Proving this required a mathematical bridge to translate the weight and speed of an object into the measurable length of a wave. This is the de Broglie relation. It states that wavelength equals Planck's constant divided by momentum. On the left is the Greek letter lambda. This represents wavelength, the mathematical language of waves. On the right is p, or momentum, the mass of an object multiplied by its velocity. This describes a physical particle. Planck's constant, h, sits at the top. It is a microscopic, fixed value that locks these two conflicting worlds of physics together. For this to be a universal law, the math must also work for the photons we already understand. We know the momentum of a photon is Planck's constant times its frequency, divided by the speed of light. When we substitute this specific momentum into de Broglie's formula, the architecture of the universe aligns. Planck's constant cancels out. The equation simplifies into the standard wave formula, where wavelength equals the speed of light divided by frequency. This mathematical harmony confirms that the same rules govern both a beam of light and a moving physical object. If every moving object acts like a wave, why don't we see everyday macroscopic items rippling through space? The answer lies in the denominator of the equation, the mass. Consider a thrown baseball. It has significant weight and tangible physical presence. Planck's constant is incredibly small, 10 to the negative 34th power. Dividing that tiny number by a baseball's mass results in a wavelength too small to measure or observe. The baseball possesses a matter wave, but its mass is so great that the wave is mathematically suppressed at our scale of reality. To see these waves in action, we have to look at a subatomic particle, like the electron. An electron has a mass near zero. This tiny value in the denominator changes the outcome of the fraction entirely. Because the mass is so small, the wavelength becomes measurable and prominent. The electron begins to oscillate and ripple as it moves. Wave-particle duality is a symmetrical rule governing every piece of matter in the universe.